Hey, hi everyone. Welcome to another episode of Robo Papers. Today, super excited. It's just me personally. I'm been really looking forward to this sharing from some of the co-authors of this project called MolmoSpaces. So we have here Omar, Rayyan, Max Agus, and Yejin Kim. Jiafei, who also a typical co-host, is also actually a co-author. So Jiafei will kind of wear both hats. So maybe Omar and Max and Yejin, if you guys can quickly share about each of you before you guys dive into the project. Maybe
Yeah,
Omar, you can
hi.
go first. Oh, sorry, Yejin. Yeah,
Oh,
sure.
yes.
Yep.
Okay. Hi, my name is Yejin Kim. I'm a research engineer here at Allen Institute for AI. And I led this project, MolmoSpaces, work over last year with our great co-authors on this project.
Max, do you want to go? Yeah, sure. Hello, everyone. My name is Omar Rayyan, and I'm a first-year PhD student at UCLA, advised by Professor Yejin. And I've been working with people at AI2 for the past around a year now on MolmoSpaces.
Hi, I'm Max Agus. I'm a postdoc here at AI2, and I'm working on computer vision for robots. And I also joined the MolmoSpaces project and have been contributing to it as well.
Okay, awesome. Well, thanks everyone for making the time. Yeah, I guess you guys can take it away. I know you have the slides.
Yeah, we'll start with a short overview of this project. And previously at AI2, I've been working on several sim-to-real projects, and specifically in navigation and limited mobile manipulation work. And one thing that I noticed, or that we noticed, is scale is very important for sim-to-real transfer and generalization. So one thing that we wanted to do was to bring that scale for manipulation domain. So we brought through MolmoSpaces 230,000 interior environments ranging from 1 to 10 rooms, and encompassing 130,000 objects with annotated 42 million graphs. And these assets and scenes are all compatible with high-fidelity physics simulators, including MuJoCo, Manuscale, and NiceLight. And in order to show that these scenes and assets are useful and meaningful for real world, we also did a robust study on and benchmarking with this large-scale data sets. And we'll detail more about this benchmarking later on through the slides. So there are four main contribution to MolmoSpaces. You have scenes, which are the indoor scenes, 1 to 10 rooms of different types of scenes. And by that, I mean we have 5 different data sets of indoor scenes, and each of them have very different specification of what they are. Like, for example, there's just like a kitchen scenes, or there could be like arcade scenes. And then the second is assets. We have 130,000 rigid and articulated objects with heavily annotated data, metadata. Next, we have graphs, which were annotated for about 48,000 objects. And finally, we have benchmark. And now we'll start describing a little bit more about seasoned objects, and the rest of them our co-authors will describe. But before we get into what we provided through MolmoSpaces, I want to talk a little bit more about what we did previously at AI2. The video that's running is Thor, AI2 Thor simulator that was built above Unity engine. One notable thing is they don't have physical contact grounding, meaning manipulation was magical grasp. If the objects were within the 20 centimeters of a gripper, then it just like snap to the gripper, and you could like move around with it, and it will just be like, fixed to the gripper and snap to it. And, because of that, a lot of the Thor families were used mostly for navigation benchmarks or very limited mobile manipulation work. And, it was expanded to other type of work like VQA and embodied AI type of work. But because if you go to next slides, and because we wanted to utilize physical simulation and like actual dynamics and context into these scenes, we decided that we're gonna export all of our scenes that we built on Unity and bring it into MuJoCo. And in order to do that, we wrote this conversion scripts, and on top of it, because now physics matter in these scenes, we had to articulate and especially the object that we decided to articulate, like drawers and microwaves and fridges, we added joints so that it doesn't animate anymore. Like before, it was all state-based animation. Now they're all physically driven articulation. We made sure that they are stable and the frictions and all the physical properties were accurate and realistic. And we did it by having a teleoperation suite, like you see in the left bottom and the left side and the right side of the videos, with a teleoperator suite of using Cited Franca. Next slide, if you go to next slide. With all this tuning, curated basically 230,000 indoor scenes ranging from 5 different data sets. And we converted this into other simulators by providing USD files on top of MGCF. So now they are compatible. You can load these files with both Miniscale and IsaacSim simulator.
Sorry, Yejin, can I have a quick question? How do you guys come up with like 100,000, scenes? Are these like kind of auto-generated?
Oh, yeah. So there were mostly, so maybe I should go through 5 different data sets that are in this table. We have one digital twin, which we handcrafted with our collaborators. And then MS crafted are 120 scenes from iThor. So they were already existing scenes from AI2 Thor that we converted. MS procs are procedure generated scene. Also, they were already existing and we just revamped it. They were procedure generated scenes, and MS proc object is also procedure generated scenes, but also using Objaverse assets, not just Thor assets. Thor, there are like 1,600 assets. Objaverse, they're up to like 129,000 assets. So there were, I think for the proc Thor Objaverse, it was sampled from 92,000. But then MS multi-type is this LLM guided procedure generated scenes using previous AI2 work also called holodeck. So holodeck is, I don't think we released through AI2 for the scenes. I think this is our first time releasing the pre-generated scenes in this scale. Yeah, does that answer your question?
Yeah, that's great. I guess I have a quick follow-up for maybe the MS multi-types. You have roughly, let's say, close to 100 objects per scene, right? Something like that. And is the right way to think about it? It's per scene is almost like a room, and so that's nearly 100 objects.
No, not it's per scene, and each scene could range from 1 to 10 rooms.
Oh, I see. So the rooms are actually kind of connected. Okay,
So there could be 10 room house, or 10 room arcade, 10 room office, museum. It could be up to 10 rooms.
Interesting. Got it. Okay, maybe I'm asking 2 questions too early. I guess maybe one last follow-up. Do you find, especially when you use the LLM, do they maybe sometimes put like objects at a very weird place where usually it's not supposed to, or they tend to be like kind of make sense? Like for example, like find a knife in like right behind the door, something like that. I don't know.
So I first want to say that this multi-type house holodeck generation was done by another co-author, so he's probably the one that's like best talk. But we did notice some weird assets being placed in odd places, like some assets being transformed. Like we saw this like small chip, the microprocessor chip, that were enlarged, scaled, used as a table in a dining room. So we found some odd pieces like that.
I want that table.
But it was a microchip with like little legs, that I guess and because all of these assets were annotated by GPT, and we used GPT annotations of what these categories are into like a synset, and then they were placed using LMM. So like sometimes it does make those mistakes. It puts odd objects in odd places.
Got it.
So I think by and large, it's all like relatively sensible. I think like one thing definitely that is the case is that the Observerse data set is like super diverse. So you have a lot of kind of strange assets in there. And actually we have to do like a ton of work in filtering assets to get like a sensible subset for manipulation. So you definitely do get strange assets, but also in like most cases, I don't think we need the scenes to be perfect in order to evaluate how good a manipulation system is. The focus here is just like having this diversity and seeing how well the policies are able to cope with it.
Makes sense. Yeah. Yeah. In some sense, maybe you want some real entropy as well. Like, the world is really messy. You could literally have a table that's exactly like you described, Yejin.
Yeah. We could have very interesting like personality that could decide. They could be on art dining table. That person or repurposed it. Yeah.
Okay, got it.
And so we just want to show the scale of this different figure that shows scale of the scenes and how like different. It's not just indoor kitchens, but it's not just indoor residential houses, but we have hundreds of different scene types and 500 of different room types that ranges from arcade, museums, office, all type of interior environments. And the next slide, we wanted to showcase the diversity of objects. So, like 129,000, they ranges from non-pickable to pickable to and also like few hundreds articulable assets that are very diverse, and among 130,000, about 48,000 or up to 50,000 are interactable.
Yeah, I have a quick question. Sorry, about also for example, the globe that you have on the right top corner. So presumably the globe would just spin, along like how you imagine. So how do you all verify and make sure like objects like that will basically articulate the way you expect it to?
So basically all the Observerse assets are rigid, so they are not articulable. So that globe is probably Observerse assets and they're fixed.
I see.
And then only articulable assets are Thor assets that we manually annotated either with a hinge or slider joints. And those are 22 categories that we hand annotated ourselves.
I see. Got it.
So all the Observers are static.
Okay, got it. Okay, cool.
And next, we're gonna talk about graphs, but I'll hand it over to Omar.
So as Yejin mentioned at the start, in the previous AI2 families of scenes, we used to rely on magic grasping, where if you get closer to an object, then it would simply stick to the gripper side. So we wanted to keep that simplicity, but at the same time, we didn't want to have something that is not physically grounded. So we wanted to provide with all of our assets graphs that you can use at manipulation time without having to compute them over and over again. So what we did is that we made a pipeline that allows you to go from any Majoko asset to around 1,000 graphs per object. And we split this pipeline into two different components. The first being for rigid objects. So as Yejin mentioned, the majority of our assets are rigid, meaning they don't have any joints. So for those, we do the default antipodal sampling pipeline or generated graphs, and then we verify them by checking that if you grasp that object and you shake it into the vacuum scene, then it would be a stable grasp and the object wouldn't just slip out of the gripper. And so we do that for all of our rigid objects. And then for our articulated objects, which you can see here in the left side image of the door, so we extract the leaf of each MDCF file, meaning in this case, if you have a door, the leaf of that door would be the handle. And then you would run this generation pipeline on the handle part to generate grasps. But we also take another step in articulation where we make sure that if you in fact grasp that handle, it will provide you with a sufficient space to do the articulation and open the joint fully and close it back again, as you can see in the video on the down side. So we do this for cabinets, doors, whether it's a linear joint or a pivotal joint for a door. And then you can compute the arc of how you want to open the door based on where the joint is and where the grasping begins. So we do that to verify that all of our grasps are working in Majoko at least. And on the right-hand side, you can see the same grasps being used in our Isaacson scenes. So they are cross-compatible with our Isaac Sim scenes and Majoko scenes. And given that we have graphs for all of these objects, then it becomes a very easy process to generate trajectories in order to do things like pick and place, picking, opening, closing of the different assets in these different houses. So you can see here some videos of either just picking or opening or a composite of these tasks. For example, in the video in the middle, you can see it using the graphs to open the drawer, pick up something, place it onto the table without having to compute any of these graphs at runtime. So it's as easy as magic graphs, but without having to like do the magic and just have it stick to the gripper when close to it. Yeah.
So maybe I'll take over from here. So another thing that we did for this project was create a small web demo in which it was possible to kind of see what our environments look like and to see some of the interactions that are possible. And for that, we used like a WebAssembly compiled version of the Majoko simulator, which lets you load these scenes in your browser. And maybe this is a good chance to just like have a quick look around in one of these simple scenes. So this is an example of the handcrafted scenes where you have like a kitchen build with a lot of cabinets that are like super close to each other. So generating something like this procedurally is not so easy. So, but like we have this data set which kind of gives a good set of examples for like dense kitchens, and then we can do tasks in these kitchens that we would potentially want a robot to be able to do. And here we are like replaying a trajectory of a robot opening a cabinet door, for example, and we can see it going to a grasp location and then being able to move the cabinet door by the handle using this grasp generation that Omar had just described previously. And maybe we have another example. So this is more of one of the LLM generated rooms. And if we have a look around this, it looks a bit like a classroom where we have like different chairs and desks and pencils. And this is maybe like a good example of kind of what the LLM is able to generate in our case. And like if we look through the door here, we see that it's like a multi-room setup. We can scroll up here as well to get a top view. And again here, we have a robot and an asset that we can manipulate. And we have like a trajectory of the robot closing the laptop, for example. And this is the type of thing that it's possible to do with MolmoSpaces to like generate this kind of data of the robot interacting with these very different scenes. This demo is also online for everybody to kind of click into and play around with. So I encourage people to look into this to get a kind of feeling for what kind of scenes and data we have. And of course, all of the other scenes are available as well to actually run in simulation. So that's just a quick demo. And so we have our scenes, we have our assets, and we have our grasp. So the next thing that we want to do is like compose all of these into a set of different tasks that the robot is supposed to be able to do. And for that, we chose the route of having specific task templates, for example, opening task and closing task and a pickup task, but having these templates be extremely randomizable. So like loadable in any of the scenes that we have and loadable with any of the assets that we have. And in these robotics papers, it's always kind of this contentious question of how do we define a task? Like, is a task like just the verb of the action, or is it like, picking up a bottle and picking up a plate? Are those two different tasks? So that's kind of not canonically defined, but we chose to go to the route of like having these task templates and having them be very randomizable. So we have our set of tasks, open, close, pick up, pick and place, pulling open a door or pushing open a door. We have a navigation task as well because we have these multiple room scenes. So we can actually tell the robot to go and find a particular item. We have a pick up and place next to task. And also we have like a proof of concept of a LLM-based task generation system where a LLM gets given a text form summary of all of the objects in a scene. And then it needs to come up with a task and also like specify a reward function that kind of matches this task.
I have a question. So maybe you can go a bit deeper into task tree, C and D versus G. So G is like the typical robotics PMP task, right? Right. So
Yeah.
put something, next to something else, pick and place. So how would that really differentiate from C and D? Like what is the difference?
So C is just pick up without placing something anywhere. D is picking up and placing inside of a container. And G is picking up and placing next to something. So for the way the reward function is defined is a bit different. So if you like have to put the pencil next to the vase, the pencil doesn't necessarily need to touch the vase. Whereas if we like place the spray can into the bowl, the reward condition is written in such a way that the spray can is not allowed to touch the table surface and only allowed to touch the bowl and stuff like that.
I see. So fundamentally, you could not say that, people like in Pi, they do like task progress. So if you think about pick and place for G, you could basically break it into like pick as 50% and place as 50%.
For pick and place, that if I'm correct, correct me if I'm wrong, Max, but the reward function is dense. So it's using how far the object is from the placement object, and it's using the contact on top of that. So it's
So for our tasks, we provide both things. We provide a dense reward function, which kind of gives you a continuous signal of how well you're doing. And we provide a like absolute success or fail criteria at the end.
And it's the same for the opening and closing tasks. It's how much you open that cabinet, how much you open that door. And for closing is how close it is to being fully closed. So you can get dense or sparse depending on your needs.
I see. So maybe what you're trying to say is that for task G, it cannot be just pushing the pen next to the bus because it's a proximity thing. So do you have to condition on doing the action of pick and place?
That's a good question. I don't think we tested pushing. I think the success criteria is just dependent on the state. It's not dependent on how you get there. So if you manage to push the pencil next to the vase and it's close enough, then that's also giving you a reward. So the success is a function of the simulation state, not like how you get to that point.
Got it.
Yeah.
And how easy, maybe you can share with the audience, like how easy it is to sort of build tasks in MolmoSpace? I say I want to build a new task. Okay. Easy.
So I think most of our tasks aren't actually like so many lines of code. I think especially the success check is mostly like 50 to 100 lines of code. So it's relatively easy to do that. But this like doesn't scale super easily. So we are also looking into the LLM-based task generation mechanism to make it scale more. But if you have a task, it should be relatively easy to just like copy paste one of our existing tasks, change a name, and adjust the reward condition to what you want it to be.
And then just to add, like if you have more than one task, you can easily compose them with each other so that like you would compose the reward functions together, which is what we do in task H here. Like, for example, it's a prepare a simple meal, and then the reward function would be opening the fridge, picking up something, then placing it onto a table, for example.
So for the H, when you talk about compose, are you doing this sort of retargeting it back into embodiment that's kinematically feasible? Is it more of like taking the atomic action?
So like, are you referring to like verifying the tasks?
Yeah. So for example, for what I see here, I think it's using the NYU Ripper that you guys develop. So like my question is that is the policy going to be testing on a rollout trajectory of like embodiment specific, or is it more of like this taking these atomic actions?
I mean, ideally we'd want it to like be done by a mobile manipulator, but in the current state, I don't think there's any open source policies that are able to like complete such a task. I think Max can speak more on that, but.
So maybe just to clarify, so there's like this distinction between like defining a task as in the success condition of that task being checked, like, have you succeeded or not? And like having this actual machinery to give you automated scripted solution to the task. So for the case of these LLM generated tasks, we are mainly just like checking, has this task been completed? And in this case, we were using teleop basically as a method to check if our tasks are being like checked in the correct way.
Yeah, I have some questions on this as well. So, I mean, this is supposed to be a benchmark, right? So, like, for example, let's take G, place pencil next to vase.
Mhm.
So for this to become a benchmark, are you guys setting up like multiple scenes that have pencil and
Okay, so
vase?
the benchmarks is what I wanted to talk about next. So maybe I
Okay.
just go
Okay,
to the
cool.
slide.
Yeah, okay.
Yeah. So we have all of these tasks, and now we have these very diverse environments. So we actually want to use this to define a good benchmark, which can test like how well do our policies work. And kind of the aim here is to have like a very difficult, diverse set of tasks, which makes it as difficult as possible to overfit on just like a specific configuration. And we wanted to really make something difficult for people to work on over like a couple of years instead of just it being saturated quickly. And basically what we did is we took this whole combination of the different types of scenes that we have and the different types of tasks that we have, and we generated some rollouts of these tasks being completed. And then we like selected all of the geometric configurations in which like the placement of the robot and actually like enables the task to be completed. So for each instance, we know that it's possible to solve the task in this way. And the policy just like needs to find that solution. So we generated the set of benchmarks. And the way we generate the set of benchmarks is in this like multi-step procedure. Like first we take a random scene, then we select a random object that we want to pick up, for example, this bowl here, and then we sample a random robot position, and then we sample a random camera position. So the idea is here to basically like have as much randomization as possible in there so that the policy really needs to be a good generalist policy in order to be able to solve these tasks. Once we have this configuration, we then kind of check if we can find a viable grasp on the object. We then see if the robot can reach this viable grasp, and then we execute the action of this grasp and check if like it's possible to get a reward for this. So after we do that, we have like this very long list of different environment configurations in which we know that the task is solvable. And then in the final state, we do this balancing where we kind of want to make sure that in our benchmark, we have as many different objects as possible, as many different houses as possible, so that it's not like super weighted to the object categories that are much more frequent in our data set. So then we do this filtering and balancing, and then we like finally export this list of task configurations as just a JSON file, which anybody can download and then like test their policy on. And they know that the task is at least solvable and see how well their policy does.
Sorry, Max, can you elaborate again? Like, how do you check if a certain task that is doable?
So we have a scripted policy solution which is able to solve these tasks, and we check if that scripted solution generates a reward or not.
Remember, we have all these graphs that can grasp poses that can pick up the objects, and then we use motion planner to get a trajectory or like waypoints to that objects to that grasp pose, and just do the rollout of that trajectory to that grasp pose. And then if that rollout is actually successful, which you'll know by the states of the object and also the context, then the reward function will tell you whether or not the task is solved.
Okay, got it. So
So we have this collection of tasks now that we're quite, it's actually quite loud for me. Can you, okay, now it's better. I don't know what changed. So we have this collection of tasks now. And then on these tasks, we can run the different policies that we have access to and compare how well these policies do. This is just some more examples of policies running the tasks here. In this case, we're using the Droid configuration because that's a big openly available dataset, which many people are able to fine tune their policies on. So we have access to policies that work in this configuration. And this is an example of a Droid configuration with one external camera. And we also have a WISP camera as well, which I'm not showing in this video. And here it's doing an opening task, for example. And so we tested a bunch of policies. So I'll hand it over to Omar for explaining how well the policies did on these benchmarks.
I have maybe before going to the benchmark, I think I have a question that maybe I think it's also for the audience. I probably know the answer, but I think it's for the audience. So one of the unique feature about iTalk back in the days was this notion of state change. So I'm not sure if you guys know this thing. Like if you crack an A into a pad, if you turn on the fire, then it does a state change. It goes from from uncooked to cook. Is that something that is considered to be included? Maybe maybe the question is it included in this stage whereby if I cut a tomato, the tomato should split into half, or something that in the future we are looking into having.
So state changes are not included at the moment, but it is possible to kind of split these things if people develop custom tasks which contain state information. But we didn't include it at the moment for any of our tasks. Yeah, so as Max described, he described a bunch of benchmarks for pick and place, open, close. We did our best effort to test these benchmarks on the current state-of-the-art policies that are open sourced. And fun fact, if you go to the previous video in the slides, Max, and the one before it, this is the recent Dream Zero word action model from NVIDIA running on our benchmark. This is the opening task, and then in the previous slide, you can see it running on one of our pick tasks. So we tested it on the Pi policies that are open source, Pi 0.5, Pi 0 fast, Pi 0, and then we also tested it on the CAP policies from NYU and Berkeley. So the CAP policies are task specific. So for the picking or closing, it's a separate policy running for each of these tasks. And then you have the general policy for Pi running in all of the tasks that you can see here. And you can see there's a good progress between the different Pi checkpoints, for example. In the picking task, it goes from 14% in Pi 0 to 20% in Pi 0 fast, and then to 28% in Pi 0.5. So you can see it's getting better over time. For CAP, we tested different checkpoint time steps from our training, and you can see it also improving across the different time steps. Now, a question that comes here is why should you trust these numbers, and why should anyone run policies in our benchmarks? And if you go to the next slide, Max, you can see that we did sim to real correlation plots to make sure that the numbers that we get in sim are somewhat correlated to what we get in real. And for our real word performance results, we used the results from Robo Arena, where we filtered the tasks based on picking, opening, and closing. And as you can see on the left-hand side, you get a pretty good correlation, a correlation number for picking, which is around 0.96. And then the ordering is followed 100%. And then you can see it's also somewhat following that correlation for opening and closing tasks, but it's hard to tell. It's hard to tell for sure because we've been using Robo Arena numbers, and then for the Robo Arena numbers, the opening and closing tasks are not that common in the evaluations that people run. So as you can see, this is shown by the big error bars compared to the picking task, where the error bars are a bit narrow. So the checkpoint in purple, this is the CAP policy, and then the others are Pi policy.
Very interesting. So you guys actually use Robo Arena as the so-called real-world counterpart. Okay, got it.
Yeah. We use the most recent data dump from Robo Arena. I know you've been running a lot of the evals from
we contributed a fair bit at Flowrobots. I do have a quick question about the earlier slide about the success rate, just on the simulation, right? So for example, when you do pick and the pick, you say, let's say 28%, for pi 0.5. Can you give a bit more color? Like this 28%, is it like what is in the denominator? Is it like 100 episodes, or is it the 100 different tasks, or 100 tasks, 100 times the same? And it, because you have multiple tasks for pig, right? So I'm just curious what is inside the denominator.
So that's an excellent question. So one thing that we wanted to do in this work is really provide benchmarks which have quite a large number of examples. So between like 1,000 and 2,000, so that it's actually possible to obtain statistically significant results. So we've tried for all of our results to include XY error bars based on like what we would expect from a binomial distribution, because we're evaluating just success or fails in this case. And it's something that's like highlighted here on the high variances that we have in the real world performance. Like if you just like zoom in on one specific task, it's really difficult to have like 1,000 evaluations of open, because like it's just like one of the attributes of your VLM that you want to test. And it's like becomes incredibly time consuming. So that's kind of one of the main reasons we are also so interested in simulation-based benchmarks, is because it's possible to like really scale them up and get more reliable numbers and get statistically significant numbers. And that's also something that we believe the robotics community should kind of also be doing a bit more. Like it's very common to see tables which don't have any error bars at all indicated, and then you're running like an experiment with like 20 or 30 trials, and actually like the variance is going to be like super high in these. So
and another thing to note is that it's not just scale, but also diversity is important to like test and like analyze, evaluate the generalization property of policies. And because we have simulation of thousands of scenes, hundreds of thousands of scenes, we can actually look at how it generalizes across different unseen novel, environments and backgrounds. So like both scale and diversity, we think is important, and simulation provides that.
Yeah, and just to add, like Max mentioned, how for the picking task, for example, we have 1,000 episodes that are like we don't repeat any task twice. It's a different task configuration for each of these episodes. But there's nothing like stopping us from just stopping there. Like as Max mentioned, it's very easy to create benchmarks that are larger than 1,000 episodes. Yeah, like but then the goal of MolmoSpaces was to get like sufficient diversity so that we can scale things up in terms of the task rather than having the same task being repeated over and over again. And then if you go to the next slide. Max, maybe you can share the leaderboard. So we still didn't publicize this yet, but we want to have like a public benchmark leaderboard that shows different policies, like evaluation on the tasks that we have. So this is still under development, but you can see. Can you zoom in a little bit, Max? So you can see.
Zoom in or click on the info.
This is good. Like I want to mention that. For each of the policies, we wanted to have something that is more than just a binary success rate number. So we didn't want to just have this policy like gives you a 55%, this policy gives you a 40%. We wanted to provide the like end user with more details than that. So if you expand the cap pick, for example, you can see the success rate per object in these tasks that we have. And as Max mentioned, we made sure that the benchmarks are well balanced in terms of the objects that they test. So you can see how the like different objects perform for each of the policies, and you can see how that compares between the different pi policies, between the Dream Zero policy below. Like for example, one thing that you can notice here is that, and if you can open pi 0.5 also, Max, you can see how like these with the George setup, the success rate of objects that are very easily pickable using a top-down grasp is very high. Like you can see it succeeding very highly in mug, cups, bowls, in both pi 0.5 as well as Dream Zero, for example. But that's the case. Sorry?
I have a question. So I think this is also something maybe to make clear to the audience, which is that one of the huge thing about Pi and also like with Robot Arena is the notion of training on the dry data set, right? So I guess like the point is that then the CAP plus Gemini ER version might not be trained on the dry data set, but then the question is this a benchmark that we want people to be able to submit any kind of system? So for example, like things like I don't know, like Box Poser, or things that is like open world task and motion planning systems where there's the notion of policy could also submit to this benchmark? Or are we just looking at VLA policy, end-to-end mapping of action to observation to action? So I mean, is this more of like any robotic system out there could potentially, be applied to test on this open world eval. It has not necessarily required to train on drug.
So we consider a policy we consider something a fair test if it doesn't use any extra simulation privileged information, which none of these policies that we tested do.
Yeah, so like our open world TEM system that does like one-time planning could potentially, if it doesn't use any pre-system, it just use a VLM to do estimation, it can solve that, could potentially go onto this leaderboard.
Yeah, I mean, at the end of the day, our like the goal of benchmarking and the goal of our policies is to be able to do stuff in the real world. And if no matter the means, if that is doable with any policy, then we consider this a policy that is fairly added to the benchmarks. Maybe Max can add on that.
Yeah, so maybe one thing to add, what we aim to do in scientific research is to have these fair comparisons between different things. And they're actually for robotics, it becomes a bit more difficult than, for example, in the computer vision case where we just have image classification. It's relatively clear, image goes out, classification probabilities are returned, and then it's clear. But let's say we're in this robotics setup and we have the droid setup in one case, and then we have a different robot come in with a different camera configuration. And then is this still a completely fair comparison to have? And I would argue, yes, it's possible to have fair comparisons, just you need need to look at the details a bit more and be aware that some of these benchmarks, you can look at these benchmarks as benchmarking your whole robotic stack, your robot configuration hardware, your camera positioning and your policy. And all of these things have to work together. And all of these things can be basically placed into our simulation and run as a whole system. And then we get a benchmark result for that. There's some details around the way we generate our base benchmarks is we assume that it's this droid configuration and that the object, and we test for the fact that the object is visible from the extrinsic camera. And then this is some configuration that we provide, and into this position of where the robot is, you can replace it with your own robot. And in that case, you don't necessarily have this visibility check, but a lot of the task setup is very similar. And then you can see if your robot could also solve the task in that case.
Yeah. So maybe another question I have, which is that, so another question I have is that instead of looking at if someone wants to test a smaller policy, something lightweight, for example, I don't know, diffusion policy, action, ACT, or something along that same category of policy, then will you guys be providing data for them to fine tune so that the idea is basically to just evaluate on the architecture, novelty of this kind. So what I'm trying to say is that if you look at benchmarks like Libra, they provide data set even for policies that is non-VLE. That means there's no large amount of pre-training. You're just doing post-training with a small fixed set of data. So would there be data set that's going to release in the future?
Actually, what we're working on at the moment is actually to use the MolmoSpaces setup to also generate large amounts of data and to train policies with that. Yeah. And we'll definitely be releasing the data with that, and that'll be coming out soon.
I guess we should have mentioned that all of these are zero-shot policies and zero-shot evaluations, and that's what we wanted to test for the, how well does generalist do actually generalize.
None of these are fine-tuned in any MolmoSpaces specific data, as done in other benchmarks usually. We wanted to stick to fully zero-shot for the policies that we tested.
And I think that's if we're talking about benchmarks and robotics, that's another point of detail. Are we talking about zero-shot comparisons completely, or if we include in this table policies that have been fine-tuned on task-specific data or data from the same distribution, I think we also need to make this very clear so that people can see what's being compared to each other here.
And I actually think that the advantage of our simulation benchmark is that it doesn't need to be fine-tuned or co-trained with the simulation data to be able to evaluate on this benchmark. You can, all these Pi and Dream Zero and CAP were trained with the real data sets, but they still work in our simulation benchmark. So you can kind of test your real world robot policy, but like really stress test it because we have scale and diversity.
Yeah, and as Yejin mentioned earlier in the talk, like benchmarks like Larbo and RoboMimic are very like saturated currently. So we wanted to have something that isn't necessarily very easy for VLAs to do because it's not in their data mix yet. I don't know if that will be the case in a few months or in a few years, but as it currently is, it's still not in their dataset mix, which is why we're not getting very saturated results for our tasks. And Max, if you can go to the other tasks on the leaderboard.
Sure. Which one do you want?
I can go to the open task, for example, and the closed task. And then you can see there's an average task, which is like the average result between all these tasks. And in this case, we only put the policies that are general in terms of being runnable within the different tasks without having to change the utility model, which is the case for the cap policy. And you can see Dream Zero here seem to perform like the best in our tasks for now.
Yeah, I think this is extremely useful. Especially like it's I think when you guys have the plot just now showing success rate in simulation versus, at least what you guys observe in the real world in robot arena. I'm curious, like, do you guys have any intuition? It seems to me like somehow for pig, it's like simulation is harder than the real world. It's like, whereas like close is easy, like it's easy to get a higher performance in the simulation than so meaning like, for example, for simulation for pig, hitting something like 60% may already get you like close to 80%, maybe like and above success rate.
So here I think it's like the question is like the benchmark result is a function of how good your policy is, but also a function of how difficult the set of tasks is that you're putting into the evaluation setup. So my guess here would be that the people who are doing the benchmarking are, like, for example, picking objects that are relatively easy to grasp, like cups and bowls, because kind of those are common objects, they work well, and they like provide a good way to test the policy, because otherwise you're going to get like very low performance numbers possibly. I wouldn't look so much at like the absolute performance on this benchmark, but more at the relative performance, because it's such highly determined by the task difficulty that you put in. And I think, we just also tried to sample some very difficult tasks, and most of the results that we're showing here in these plots were on like relatively easy subsets of tasks. And we also have a much more difficult set that we will be releasing as well, which will be like an even more challenging test for these policies.
Yeah, but I guess so long there's a very strong correlation, I think that's the thing that matters.
Yeah.
That's really
And we
cool.
did definitely notice that like closing is much harder than opening task. Like if you like bump the gripper, even if you don't like close it fully with the trajectory, because all of our rewards are like state based. If you push the drawer or cabinet doors.
Closing is just like much easier. You just have to like move forward and collide with whatever, and that collision is enough to push it back. Whereas for opening, you really need to grasp,
like pull it. Yeah.
Grasp the handle or something like that to get it open.
Yeah, and like one of the failure also comes from slipping, like the gripper slipping from the handle. So like having a stable robust grasp and then like pulling the drawers or doors, it's much harder than closing. And picking because it's articulated, so the joint is constrained.
Max, if you go to the 20th slide, there's the distribution evaluation. Yeah, so one more thing that we're able to test on MolmoSpaces, given the scale that we have, is like to do distribution evaluations where we vary different factors in our tasks and see how the policy's performance compares under these changes. So for example, we tried different, so this is for the pick task. We tried different combination of verbs to prompt the pi policy, pi 0.5 to be specific, under different like prompt examples. So for example, we tried pick up the object and eat it, pick up the object and place it on a plate, and then the last one is like put the object on a plate. And in all of these like different prompt samples that we used, we had the same exact task. So even though like in one of the prompts we had pick up the object and place it on a plate. We didn't really have a plate in the scene in most of the cases. We just wanted to test how like different verb combinations result in a different like performance in the picking task. And the number that you see in the legend, which is like 177, this is the frequency of these verbs occurring in the droid dataset. So for example, the put
There's no
has
eat
occurred
in droid.
Sorry?
There's 0 eat in droid, I suppose.
No, like this is there's 0 tasks where like eat came after pick. And then there's like 177 tasks where it was only pick without any other verb. And then there's 1,600 of pick then place coming after it. And as you can see here, it's very clear that like that. I mean, it's kind of an obvious result, but it's nice to see and validate that like the more frequent prompts, like when you use prompts that are more in distribution to the droid dataset, you get a better performance. And especially the earlier like checkpoints, like pi0. For example, in pi 0.5, this is not really as important, probably because there's a bigger dataset in the mix that they use. But this is more common in earlier policies where they are more heavily trained on droid data alone. And go to the next slide. You can see other tests that we did where we sweep, for example, the joint initial joint position of the droid setup. I mean, I'm sure you've been running Robo Arena for quite some time. Like the 0.0 like variation in the joint perturbation graph is where we use the exact same initialization that is used in the droid telop data collection like setup. And as you can see, the results there are better when we are closer to that distribution than when we like initialize the droid to start from something further away from that. Again, another thing that we swept was the light, like the light intensity. And as you can see, this doesn't make as much of a difference. And that's probably because we can easily do these augmentations in your data loader, which are like, and it's not as easy to do things like joint augmentations, which is why we see a bigger like fall in success rate in those sweeping. One more interesting result that we found, which is on the bottom right corner, is we tried to include the third-person camera for pi 0.5, and as you can see, it doesn't really make that much of a difference. Like it does make an 8% difference in success rate, but it doesn't really drop down to 0, meaning that the pi 0.5 policy is like, in a way overfitted to the wrist camera compared to the third-person camera, where if you just occlude the wrist camera with 100% probability, you would go down to 2%, which is a bigger jump than if you do that for the third-person camera. And then one more plot is the one on the bottom left corner, is where so the CAP policies that we mentioned, the contact anchored policies, these are conditioned based on 3D points in space, and we try to increase the noise for these initial conditioning. And as you can see, there's a big drop in success rate once we do that. It goes from 61% to 23% once we add a noise of 1 centimeters from the actual object position.
Oh yeah, 9 cm is quite big. It's like a full palm. Okay.
Yeah,
makes sense. What is this light multiplier on the top right?
So the 1.0 is where we have the standard lights that we have in our scenes. 0.5 is where we dim the lights to 0.5 of what they are at. And as you can see, it doesn't make that much of a difference. Like it's still around 28%, 29%. And yeah, as I mentioned, this is probably because there's a lot of like brightness augmentations and the data loader for these like policies training.
I think on top of the findings that we see from doing this distributed shift studies is that like because we're in a simulation and we have all this scale, you can really stress test different components and how that affects the performance. And like anybody can, come up with an experiment and use our benchmark and our simulator assets and scene to like come up with those studies.
Yeah, one more thing to add is that like we have like a synchronous way to run these benchmarks where you can run it in multiple threads to get results pretty quickly. Like for each 1,000 episodes with sufficient like parallelizing, you can get results in around an hour or less, depending on your resources.
Gosh, yeah. I'm just thinking to do it 1,000 times in the real world, it's gonna take days.
I'm sure. I mean, you've been running a lot of Robo Arena results. I'm sure.
Oh yeah.
Oh, actually, I think it's really cool. I think MolmoSpace is really cool. Not because I'm author on this paper. What I'm trying to say is that there's so much things happening, right? Like think about it. There's a benchmark. There's like a bunch of assets that's physically realistic, well tuned. You're able to port it into mature code, many scale. You're able to generate graphs. Usually, each of these is a paper on its own. But now you're putting everything into this one paper. So, like, what is that? Like, let's say, imagine if someone who is have no idea to simulation, do you think that this is the one that you sort of start off with? Looking into exploring, looking into building things out of it. Like what do you want to be like the takeaway message for anyone who wants to use MolmoSpace? Like do they think of this as a one-stop shop towards everything in simulation? Is that the goal?
Well, I mean, certainly there are limitations to our MolmoSpaces. It's, like for example, most of our assets are rigid and we provide only a few thousands of articulable assets. But still, certainly like people can use our scenes and assets to generate data, to evaluate their policies, evaluate their, if not policy, their systems of robotic systems. And this could definitely be a first stop for anyone who want to just like learn using simulator. We have quick startup, like we have in our repo, we have a quick startup guide of like how to download our assets, how to load our scenes, how to visualize those graphs, and more. And then in the future, we're planning to release through different projects. Through a follow-up projects, we're planning to release more on like a scripted planner policies and the actual data set that you can use to train the model on your own. But with this release, we definitely want people to use our assets and learn how to play with it and also try evaluate your policy in it. I think that would be very nice.
Yeah, so maybe one thing to add is that like in this project, like when I was working on this kind of stuff previously, it's very difficult to kind of get a set of everything that like fits together in a good way. Like even if you like have a large set of objects, then you also need to like get text descriptions of those objects in order to be able to generate like VLA instructions for the tasks. So there's all of these like small steps that we did for this project, which if you like add them all up are quite a bit of work. So this is definitely good because we've put in a huge amount of effort into like having all of our assets, having good text descriptions for all of them, having like good convex meshes so that it's possible to run them in a simulator, and like tuning all of the physics for our articulatable assets and everything. So we didn't talk about it that much in this presentation, but like a big amount of work went into like making all of these parts fit together well and be like tuned in a good way so that they end up working quite well to achieve this overall task. So I think it's definitely like a very good place to start. And as Yejin said, we'll be releasing much more additional infrastructure to make working with this set of assets easier in the future as well. So I encourage everybody to use it.
Yeah. We call it end-to-end ecosystem because of exactly what Max said. We have all this little part that like plugs in really well together, that like annotated graphs for these objects, so you don't have to use graph proposals. You can just use our ground truth grasp. You have all this description of text, so you can create your own VLA instructions. And
we hope that people like build on it to do even cooler stuff. Like we know, for example, that in like sim to real has been limited to locomotion due to the like limited diversity of sim assets. So we hope that people like start using it in these areas to get like good sim to real transfer of their policies, and hopefully we get to see more like manipulation policies compared to locomotion policies transferring from sim to real.
And everyone is welcome to contribute. Obviously, add your robot. If you're using a different robot system than Franca Droid setup or Rainbow setup that we have, it's possible to add new robots as well and use your assets. One of the things that we added for our benchmark was to like add a new objects. So if you have a custom objects or like data sets that you want to use and place it in our scenes, it's possible.
And yeah, maybe one more thing is, because these are like big multi-room houses, it's also possible to do mobile manipulation things in them and more long horizon things. And what we have so far is like navigation policies and manipulation policies like side by side. But definitely like the next step is to go to mobile robotics, because like as we see in manipulating these articulated assets like drawers and closets, it's very difficult to do with a stationary robot just because you reach the limits of the workspace so quickly. So that's definitely the direction that a lot of research is going to be headed into, and this is like a very good environment in which to do that kind of research.
Yeah. Hopefully we get more like open source mobile manipulation policies that we can test in the future in our benchmarks.
Yeah. Well, yeah. Well, first I want to congratulate you guys. Like, it seems like, well, how long did the whole team sound? Is it like, it sounds like a full year, is it? It's like so much more.
It's more than a year.
Oh gosh, yeah. But yeah, it's. I mean, like Yejin, like you say, yeah, it's almost like really end to end. You know, 100 over 1,000 scenes, you know, tens of thousands of objects. Like just that alone is already plenty of variations. Yeah, I think things like this, it, yeah, I mean, I think having the variety of assets is a big one, but also making it easy for people to build on it and, you know, contribute and maybe set up their own benchmarks. Like once that's unlocked, then, you know, it should be very, very valuable. Um, yeah. I'm glad that the Robo Arena or whatever thing, the real world stuff that we're doing, you know, have to help you plot this thing, you know, because yeah, ultimately it needs to work in the real world. But yeah, very happy to see that straight line.
Yeah, like we'll I don't think simulation benchmark will replace real robot benchmark, but I think it's a good complementary thing to like real robot benchmark can do certain things really well and like shows promise like obviously we want it to work in the real robot and that's our final golden like
Yeah.
star. But like having a complementary simulation benchmark that we can really stress test, I think is really valuable as well, and we'll go hand in hand together.
Yeah, absolutely. Because I think that, like, you know, obviously everyone know that like do real world eval is extremely costly, extremely time consuming. So we really have to take care of these resources, and I think one way to direct that resources to have much more informed decision of what eval to test in the real world. And so I would say maybe going forward, like what we test in the real world should be based on like what is at the cutting edge of like, okay, what is still kind of failing in simulation. Maybe that's where we test those in the real world to test the limit at the margin instead of testing things that maybe is kind of already work, you know, like maybe pay is no longer a thing, or maybe we try some really difficult to grasp object, right? Instead of trying the simple toys things, you know, easily graspable things. So I kind of feel that it also inform like for maybe people like me who also do more the real world eval stuff to how to allocate those real world resources more carefully. Yeah, this is awesome. Is that the last slide? Just now the last one.
No, I just went back to the sim to real correlation because you were talking about it.
Okay.
And yeah, thank you by the way for all of the work that you did testing robot policies. It was
Oh yeah,
helpful.
no, it's yeah, just yeah, yeah, yeah. I'm glad to be of help. Yeah. Yeah. Okay, cool. I guess maybe as a maybe to wrap up the episodes, like a couple of questions we always want to ask. I mean, you guys already mentioned some, you know, follow-up works that you guys will be publishing. But is for this particular paper though, like or this project, is there anything that you not expansion of scope, but maybe could you wish you have a bit more time to go a bit more deeply? Like for example, could you have like done instead of 1,000 to 2,000 episodes, you could have done maybe tens of thousands because you definitely have the assets and the scenes. I was just thinking, and it's relatively 1 2 hours to get the benchmarking done. Why not do more? Like I don't know, it could be something like that. Like could you talk about things that if you have a bit more time or a bit more resources, you would gone a little bit deeper? Like what would be some areas?
So I would say definitely we could have we're still working on the leaderboard and just like communicating well, like what is the performance of different policies and just like providing something to make also people motivated to use a benchmark. Just like having a very good set of different policies and how well they perform is super helpful to people writing a paper because they don't necessarily want to themselves run like 5 different benchmarks and like 5 different policies all of the time. So we want to kind of provide that reference point definitely. As to the question of like why 1,000 or 2,000 episodes, like I think the sim to real correlation plot shows it quite well. Like if you get to that level, you are like at plus or minus 2% performance, and that's already kind of enough to give you like a good indication of like, is this policy better than the previous one? And I think like only if the policies get like super close to each other, then we need to run more in order to be able to tell if they're really apart. But I think we're still in this phase of like progress happening really quickly and the difference in performance being quite big. So that like hasn't been necessary yet at this point.
I think if I had more time, one thing that we really tried was to make this compatible with across Mujoko, Isaac Sim, and Maniscale, because we wanted to provide and capture all of the audience in robotics community who use simulators. But one of our main work was using Mujoko. So I think at the end of the project, we were kind of like converting to USDA and then running in Maniscale and loading in Isaac Sim, making sure it works, and then running some tests. But we didn't have time to do like as comprehensive testing of physics stability and collisions and all that stuff, or articulation tasks as we did for Mujoko. So I think if we had more time, it will be definitely just like making sure our scenes are really. I mean, we did check like several thousands of scenes per data sets, so they are good. But I think we would have expanded that and made it as comprehensive as we did with Mujoko and Jin.
From my side, it's adding more policies that are open source. There's a lot of policies coming out these days, and we are continuously working on adding them to our benchmarks, and hoping that people will start adding our benchmark to their like loop of training evaluation themselves. But yeah, if anyone wants help in adding this benchmark to their policies, I'm more than happy to help them set it up. You can reach out to us and really like happily help you guys set it up.
Yeah, the same thing goes for the whole setup. Like we've got it hosted on GitHub now, and like try to use it and feel free to reach out with any questions.
Yeah, happy to help.
Okay, that's awesome. Well, again, thank you so much for your contribution, and basically pretty much sharing everything, openly. It sounds like a lot of work. Yejin, when you say you wish you have done more, but it sounds like you already did a few thousand scenes. That's already not small. I thought maybe you only did thousands. Okay, then, but I mean, that's already like So yeah, kudos to you guys. Thanks for all your hard work and again putting it out there. Maybe as a final question, like the one we usually wrap out, are there any like cool papers that you guys like kind of read recently you want to give a shout out to? It doesn't have to be strictly about simulation, but you're kind of interested. Yeah, if you're going to give a shout out, feel free to do it now.
Maybe one paper to mention that came out recently similar to our work is Scenes Mesh, and I looked at their results and their environments looked very nice. It seems that they don't yet have like the same kind of scale of scenes as we're providing, but they managed to get the detail right really well. So that was impressive to see, for example.
Scenes Smith. Okay, cool.
Yeah, from TI, yeah.
I will probably give shout out to Dream Zero paper that they reached out, and Omar had ran a lot of the evaluations on Dream Zero, but it was pretty impressive how well they're doing. It's the only world model based policy that we tested. Everything else is VLAs. So we're glad that or not everything else, but like Pi is VLA and then there's CAP. So it's kind of like nice to have another architecture variants to be put on our leaderboard and compare.
Yeah, that's awesome.
I was gonna say from my end also Dream Zero. It's been nice to see it running zero shot in our benchmarks and like beating the other policies.
Interesting. Yeah, we're having a chat with them tomorrow actually. I think tomorrow.
Really?
Yeah. Xiong is coming. Yeah. We're very lucky. We have like researchers like yourself who willing to spend time to come on the pod. But yeah, we're definitely looking forward to that one. Yeah, and also awesome to see that they're doing so well in your benchmark.
Yeah, Omar, I think you showed the plot where you were showing the performance over time, and then you said like, "Oh, we only have to wait for 2 years in order to be saturated
Yeah,
in
yeah.
performance again."
Like yeah, we got a plot where it's like the x-axis is the release date, and then the y-axis is the success rate, and it has been going linearly since 2024, since the first Pi Zero policy came out. So we're on a good trajectory so far, I would say. We have a good release date to performance correlation.
Yeah.
Yeah.
Yeah, but that's exciting at the moment. Like you see the progress is happening so quickly at the moment. It's really an exciting time to be doing this research.
Yeah, I think also it's very timely to start to have like for the community to take like benchmarking really seriously, because like you say, it's happening faster. You know, we should track the progress. I always feel that like in robotics, like every other paper is a SOTA paper, you know. So we probably desperately need some credible benchmarking. You know, both simulation and in the real world. Yeah. Yeah. So okay, thank you so much for making the time, guys. Definitely looking forward to your next one. Then please come on again when you guys release the next one. And of course, everyone listening in, you know, everything is on the GitHub. Please contribute. Especially if you're building models, like you try this out and get on the leaderboard. Leaderboard right now have what I think six or seven models maybe. Hopefully, hopefully we get to dozens soon. Okay, thank you so much. So yeah, well, till the next time. Thank you.
Yeah,
Thank
thank
you.
you. See you soon.
Okay.
Bye-bye.
Yeah.